So we already heard that stack too deep is one of the most pressing issues, but I would say another pressing issue that I put in the subtitle here is the UL optimizer performance, or generally the performance of SOC. Whenever you compile a bigger project, you might have realized that it can take tens of minutes, if you're unlucky, to actually get the bytecode out, which obviously is a long time, and to increase throughput of developers, but also get rid of this annoying problem. We are investing in a new backend, which is based on SSA-CFGs. And yeah, so let's see what that is all about. First, I want to give a small motivating example. Here we can see some UL code. So this isn't straight Solidity code, but the code that falls out of it if you go through its internal representation. And that internal representation is relatively close to the EVM. So what it does, it stores a memory guard address at 0x40. It has a function which has many return values. I put an ellipsis here, but it's, what's that, 18 return values. Then we simply take these 18 return values and store them to storage. Now, if we try to compile this through SOC present day, we will get one of these pesky errors, which is called stack too deep. And that's kind of the high-level view of what you can see as a user. But in order to determine what we can do to get rid of it in the end, we will have to zoom in a little bit and go deeper into the internals of the compiler. So what happens if we do -- viaIR, or if we go through UL? We have at the left-hand side Solidity code, which some of you may be familiar with, and then the Solidity code is through a translation layer transformed into UL. So that is this intermediate language between EVM assembly and Solidity. And then potentially in the middle, we have a UL optimizer, which will at that level of abstraction perform some optimizations which will give you gas benefits and such, and then we end up at EVM assembly. The stack too deep error itself occurs at the step from the UL optimizer to EVM assembly, or from UL code itself to EVM assembly. The name itself already hints a little bit at what it is. It is a problem with the stack. So the EVM is a stack machine, and UL itself doesn't really know anything about the stack yet. The transform to EVM assembly, though, will then have to deal with the limitations and benefits that the EVM stack brings. Okay, so let's look at that a little bit. And in particular, what I want to look at is a step that we call stack layout generation, or sometimes it's also called stack layout scheduling. And that is a step that will, for each function and for each built-in call, where a built-in could, for instance, be here an mload on the right-hand side, we will prescribe a specific layout of the stack that we expect the EVM state to have at that point in time when executing the bytecode. So if we walk through this example real quick, we have a function f, which takes two arguments, v0, v1, and it returns v4. That means initially we can assume the stack top. And if I look at these representations of stack, it's important to keep in mind that the rightmost bit of it is the top. So v1 is below v0. We have a stack v1, v0 with v0 at the top. And then we want to execute the first instruction, which is an mload of v0. And since v0 isn't used anymore downstream, we can simply emit the mload opcode, and the v0 is going to be replaced by a v2 symbolically. Now, afterwards, we want to mload from a static address 42, right? This is just a made-up example. So we will have on the left-hand side the preparation of that operation that we want to execute, which is going to be a push of the constant 42. Then the stack state is going to be V1 at the very bottom. Then we have the V2, which is the thing that was loaded previously, and the 42 that we just pushed. Then we can execute the second mload. Then the 42 is going to be replaced by a V3 symbolically. We swap them around for a add that we execute afterwards. And then in the end, we want to return V4. And after the add instruction, the state is going to be V1, V4, which is one V1 too many. So we will have to swap one pop, and then we can return from the function. That's kind of what stack layout scheduling looks like. So for each instruction, you prescribe a layout of what that instruction needs in terms of shape of stack, symbolically. Now, not every function is just a single block, but you have multiple blocks in there. Here, for instance, we have a function which contains an if condition, and that if condition is going to either reach a reverting branch, or it's going to return. So we have AB as argument, C as a return value. And then suddenly we not only have stack layouts that we want to prescribe for individual operations, but we also have stack layouts that we want to prescribe for transmissions between blocks, or rather block input and output layouts, which are also going to have to be generated. So now, in order to achieve all this, we have a component that we call the stack shuffler, which takes a specific input of stack, which is this symbolic representation of stack, and then we want to achieve a target stack, which has a ordered stack top, which is precisely the arguments that the next operation is going to need. And it has an unordered liveness information informed tail end. And this tail end then simply contains the information what we need downstream symbolically after the arguments of the next operation have been consumed to carry on without loss of information. So where does this stack to deep come in? And here I have a small example. So we have a stack with a V1 on top and then all the way down to V18. And we might want to change this shape of the stack symbolically to the V18 being on top and the V1 being in the bottom. If we cannot remove any of the stack slots in between, because that would cause us a loss of information that we couldn't recover from symbolically, then we are in a so-called stack to deep situation where we would have to essentially execute a swap 17, which means I will exchange the V1 with the V18 directly. And that, as of now, doesn't exist in the EVM opcodes. So we can't do it, essentially. And the idea of memory spilling is then, let's park a few of these symbolic values in memory at specific addresses, so we can, in fact, remove them from the stack, so we can work around this limitation of only being able to swap around the top 17 elements of the EVM stack. So here is this example explained if we did have memory spilling. And supposedly we have spilled the variables V18 and V17. In order to swap around V1 to V18, we would first pop V18 and V17, which frees us enough space to perform the swap 16, which brings the V18 down to the last slot. And then through M-loading V18 and V17 back onto the stack, we can achieve the shape that we need. So it's really as simple as that. This is provided that we know that we have to spill V17 and V18, but we also have to figure out that first of all, and then also where to put it. And that's basically what it is about with the new backend. And then I also alluded to it in the beginning, we have long compile times. So here's a little bit of a historical view on it over a couple of projects. I don't want to go into too much detail, but on the x-axis, you can see the last couple releases. So 0820 through 0835 plus the current development version. 0820 was in 2023, if I'm not mistaken. And since then, we have improved the performance quite a bit. So up to 2 or up to 4 times the performance we had back then, 2 to 4 times. Still, it's too slow, though. And as this graph already shows, different projects have different speedups. So in the end, it's all a question of access patterns and how do I optimize what, and figuring out where the bottlenecks are. Looking at that a little bit more, if you call Sol-C, which is the Solidity compiler viaIR with the optimized flags, and then you trace through the program and emit a few timing information, then you can see that about 80% of the time is spent in the UL optimizer. And this is statistics I made by looking at Sourcify and compiling about 6,000 contracts on it and just checking, where is the time spent. Turns out that the UL optimizer essentially has 2 problems. The first problem is of algorithmic nature, which is something that we can deal with different representations, which is this backend about. And the second problem is that it was never written with proper benchmarking in the back of people's heads. I mean, it is an old project. So we are getting an opportunity to do better now with a new backend, which actually is easier to do than trying to rewrite what is currently there. So that leaves us with SSA-CFG UL. And SSA and CFG are 2 nice acronyms that I want to explain a little bit. So SSA stands for Static Single Assignment Form, which means I will transform a piece of code. So on the left-hand side, I have a non-SSA version, which is y equal 1, then I set y equal to 2, and then I set x equal to y. And I will translate that into a corresponding SSA form where each variable is assigned exactly once. So everything is constant. We have, instead of 2 variables, 3. So we have to pay a little bit, right? We get more variables, but then everything is constant. V1 is constant, V2 is constant, and then V3 is also constantly set to V2. This is a shape of, or a form of representation that is battle proven in many major compilers, such as LLVM or GCC. And in particular, it enables us to speed up the optimizer by having more efficient access to dev use queries and use dev queries and all that kind of stuff. So here are the algorithmic gains. Then the second acronym is CFG, which stands for Control Flow Graph. As initially described, not every program is a single block. If you have multiple blocks, you have to reflect that somehow. And one way of doing that is a control flow graph. So on the left-hand side, you have a simple if flow, which has 3 different blocks, A, B, C. The B block is a condition, C is then the post after the if. You can do similar things with for loops, where you have a cycle between A and B, or rather an edge from A to B, and then what we would call a back edge from B to A, with a loop post C, or on the right-hand side, a little bit more complicated example, where you would have something like a for loop, which has an additional break condition in it, which allows us to break us out from the body. Now we can throw this all together, and this is then what the SSA-CFG representation of UL looks like. Yeah, I hope you can read this properly. So we have an entry block, and then you will notice that there are not only ordinary variables in here, but there are also so-called phi functions. As I said before, everything is constant, but if everything is constant, how are we going to do loops? How are we going to set a value of a variable conditionally, right? And this needs a sort of trick of functions which are defined on the control flow graph itself. These are these phi functions, which essentially tell us, let's look at an example here, phi1, for instance. If the control flow came from block 0, which is the entry block in this case, then the variable phi1 is going to have the value 0. And if it came from block 3, which is kind of the back edge from the outer for loop, then the value is going to be whatever the value of phi11 is. So like this, you still have constant variables everywhere, but you have this additional construct of phi functions, which are these functions on the graph structure of the program itself. Now, doing the SSA-CFG representation based on Yule allows us to do stack layout generation slightly different than it was done before. So if I hold them side by side, what we do now with this new backend is we go top down. You look at the entry of a function call, you look at the entry of the program itself, and then produce essentially top down, really in a topological sort style of way, or topological order style of way, the stack layouts. We base this on explicit liveness analysis. Liveness analysis tells us at which point of the program is which variable live or needs to live on, and which variables can I forget about. This is a crucial information for stack layouts, right? Because I need to prune stuff away. And then if I have control flow joins, for instance, when I have a variable whose value is set conditionally, then I know by the propagation of information that all information is going to be available at both parents of the block that I looked at. And then I can simply pick one, for instance. So this is a very constructive way of producing stack layouts, which is also going to be good for us because it produces code that is actually maintainable. Compare that to the current viaIR, which doesn't have an SSA form. It uses a bottom-up stack layout generation because of that, which means you look at function returns, you look at reverts and stuff, and then say, okay, at this point in time, that's my current stack layout, and I'm going to propagate it back up. That is done because you don't have an explicit liveness analysis, and in particular, you then will only see the definition of a variable after you have seen its use. This also means if I have control flow joins in the bottom-up direction, then I cannot assume that I can just pick one of the two, but I have to actually merge two stack layouts, which is a very expensive and opaque operation. So we're winning there. And then essentially to the meat of it, so the current viaIR pipeline has something that is called the stack limit evader, which operates on the Yule AST. And the Yule AST is being transformed by replacing expressions through M loads and M stores. So the stack to memory spilling happens on an AST level. This doesn't have anything to do with the EVM yet, really, other than Yule being an EVM designed language, so to target EVM, but it doesn't really need any of the EVM specifics at that place. If we look at what the SSA form enables us to do, we can simply say, okay, if I do the stack layout generation, I don't even have to touch the AST anymore, but I can defer the stack to memory spilling to the point in time at which I actually need to access something, to the point in time at which I actually would have to spill something to memory, which is precisely stack layout generation, a step after the Yule optimization. And in this case, it's then going to be on demand. So if the stack shuffler, this magic component which transforms one stack layout to the other, gets stuck and cannot continue anymore to achieve the desired final form, it's going to trigger the spill. And the spill then translates to a dupe and an M store at the definition side, because we only have one definition of a variable, and that definition is constant, and that is going to go into memory, and that's it. And then later I will push the address and M load it back. And this is then done in a loop until we can actually generate the code, and there's no more stack too deep. So yeah, going back to the initial example, the SSA-CFG pipeline, as Jacob already mentioned in his talk, is available under an experimental flag in the latest release. The memory spilling is not yet part of that release. It's going to be part of the next release. It's merged into the current developed version. And if you take this example, then you can actually compile. There are, of course, caveats. Yeah, whenever we have situations that we think that there are no caveats, we will find them anyways. And one of them is that we cannot really handle recursive core chains. If we have a recursive core chain, we don't really know where to spill in a finite amount of memory. You would have to bound that somehow. You would need stack frames and such. So we are intentionally saying, if we are in a recursive core chain, then we cannot do memory spilling. And if you do write inline assembly in your Solidity contract, then these regions have to be marked as memory safe, which means you as the developer promise that you don't mess with the Solidity internal memory model. That means, you yourself take responsibility to some degree that you don't destroy the internals, because if you do, then all bets are off, essentially. So these are the two caveats. Then the IR itself, that's kind of, if you're interested, for this many return values example, looks a bit like that. You have the memory guard, which is a property of the entire contract at the very top, which is set to some value, that value signifying from where in memory the quote-unquote user space begins, so which memory is freely available for use. And then there are instructions. So v0 is set to the memory guard value itself. v1 is a constant. Then we have a built-in call to mstore. And then we call into this user-defined function many, which is v3, and then return a tuple value, which is projected down to the individual components of that tuple. These are these projection instructions. And in the end, we have a bunch of S stores emitted. Yeah, and if you look at the spill info, you can see that indeed exactly two values have been spilled to memory, v5 and v21, which is then, as I explained, demand-driven by the stack layout generation phase. Okay, so what's the current state? I already said it's on develop, including memory spilling. We're still ironing out a few kinks, but under an experimental flag, you can use it, you can try it out. The bytecode performance of this new backend is mostly on par and also surpasses the current viaIR pipeline at times. And the compile times, as we haven't begun porting optimizer steps, hasn't improved yet. So currently would still run Solidity code, viaIR, Yule optimizer, which is the slow bit, then transform this optimized Yule into the SSA-CFG representation, which then triggers code gen. Then next up is stabilization of this pipeline. We have the experimental flag for a reason, which means you can try it, but If you want to use it with grown-up money, then please don't. Or you have to make absolutely sure that everything is correct in the end. The stabilization phase is supposed to alleviate that. We want to have thorough code reviews. We are actively doing fuzzing on this pipeline. And then finally, there are a few remaining bumps in this stack shuffler, which is a greedy algorithm in which it is easy to sometimes get stuck in loops. But we are ironing them out. And then finally, and this is the more midterm prospect, we will port over the optimizer steps and actually hopefully get a compiler which is fast. Yeah, that's all I got. Thanks.